Imagine a planet so reflective that it doesn't just bounce back sunlight, it becomes a second sun, where astronauts would go insane trying to land because they'd see 10 copies of their own ship, where you could literally cook a world with its own reflection. Welcome back to Planetary Possibilities. I'm Aria, and today, we're stepping through the looking glass. Last week, we explored diamond rain worlds, planets where the sky literally crystallizes into gemstones. This week, we're getting weirder, because mirror worlds aren't just about pretty reflections. They're about physics going haywire in ways that would make landing on them a nightmare, and observing them from space absolutely mesmerizing. Now, when I say mirror world, I'm not talking about a planet made of glass. I'm talking about worlds with such specific atmospheric conditions, or surface properties, that they reflect 80, 90, even 95% of the light that hits them. For context, Earth reflects about 30% of sunlight. We call that our albedo. Mirror worlds would have an albedo so high they'd be visible from neighboring star systems, shining like beacons in the darkness. And here's the thing, we think they might actually exist. Let's start with the most alien of them all, the glass atmosphere planet. Picture this. You're approaching a planet roughly the size of Neptune, about 4 times Earth's diameter, but instead of the familiar blue and white clouds we're used to, this planet shimmers. The entire atmosphere looks like it's been dipped in liquid silver, with swirls of translucent white and pale gold. As you get closer, you realize the atmosphere isn't smooth. It's textured, almost granular, like someone took a trillion tiny mirrors and suspended them in mid-air. Here's what's happening. This planet orbits close enough to its star that temperatures in the upper atmosphere hover around 1000 degrees Celsius. At those temperatures, silicon dioxide, yes, the same stuff that makes up sand and glass on Earth, doesn't stay solid. It vaporizes. But here's where it gets interesting. As these silicon dioxide molecules rise into the cooler upper atmosphere, they condense. Not into droplets like water would, but into microscopic glass spheres. We're talking nanometers in diameter, smaller than a wavelength of light. These glass nanospheres are so small and so perfectly formed that they don't just reflect light, they scatter it in every direction. And because there are trillions upon trillions of them suspended in the atmosphere, the entire planet becomes one enormous, multi-layered mirror. This isn't science fiction. In 2018, astronomers discovered an exoplanet called LTT 9779b, a Neptune-sized world that reflects 80% of its star's light. That's higher than Venus, which was our previous record holder at 75%. The secret? Metallic clouds. LTT 9779b is so hot that titanium and silicates condense into reflective clouds. Our glass atmosphere planet takes this concept further. With the right atmospheric pressure and temperature gradient, silicon dioxide could absolutely form these mirror-like aerosols. And the effect would be stunning. Multiple phantom suns scattered across the sky. Light bending and refracting through layers of glass particles, creating halos and light pillars that would make our Earth auroras look like a cheap flashlight by comparison. But here's the really wild part. On a planet like this, you wouldn't just see one sun. Depending on where you were in the atmosphere, or on the surface if it even had a solid one, you might see 5, 10, 20 copies of the same sun, all at different angles, all equally bright. Your sense of direction would be completely obliterated. Okay, so that glass atmosphere planet is wild. But let me introduce you to something that hits different. Something quieter, and somehow more unsettling. The ice mirror ocean. Imagine a rogue planet, one that's been ejected from its solar system and now drifts through interstellar space. No sun, no warmth, just cold. So cold that any water on its surface has frozen into ice. But not just any ice. This planet's surface temperature hovers around -100 degrees Celsius. At that temperature, with virtually no atmosphere to create friction or weather, any liquid water that existed would freeze into the smoothest ice you can imagine. We're talking atomic-level smoothness, like a frozen mirror stretching across an area the size of Earth's Pacific Ocean. Above this ice, a thin atmosphere rich in metallic particles, maybe aluminum oxide from ancient volcanic eruptions, now condensed into a reflective haze. So you've got a mirror surface below and a mirror sky above. How it works. Light, whether from distant stars or the faint glow of the galaxy itself, hits this planet and gets trapped. It bounces off the ice, reflects off the metallic cloud layer, bounces back down, reflects again. Over and over. Physicists call this a Fabry-Perot cavity, basically two mirrors facing each other with space in between. And when light gets trapped in one of these, it creates standing waves, interference patterns that can amplify certain wavelengths and cancel out others. What would this look like in person? Colours shifting as you walk, bands of light, red, blue, violet, rippling across the ice like someone's playing with the saturation settings on reality, and complete, perfect silence. No wind, no waves, just you and infinity stretching in every direction. Why it's scientifically possible? Rogue planets are everywhere. In 2021, researchers estimated there could be billions of them in our galaxy alone, worlds ejected from their home systems during formation or through gravitational interactions. Many of these would have started as ice giants or water worlds. If they retained a thin atmosphere with the right composition, metallic particles from past volcanic activity, for example, you absolutely could get this mirror effect. And here's something we know for sure. We've found ice on Earth that's this smooth. In deep Antarctic cores, ice forms with almost zero surface roughness when there's no thermal cycling. Scale that up to a planetary ocean with no weather, no tides, no tectonic activity, you've got your mirror. But standing on that ice, you'd see yourself reflected below. You'd see yourself reflected in the clouds above. And if you looked out toward the horizon, you'd see infinite copies of yourself stretching away in every direction, getting smaller and smaller until they vanished into the curvature of the planet. Lonely doesn't even begin to cover it. Alright, we've done beautiful and eerie. Now let's talk about something that breaks the rules entirely. The planet that heats itself with its own reflection. This is a rocky world, about 1.5 times Earth's size, orbiting terrifyingly close to its star, maybe 10% of the distance between Earth and our Sun. That's closer than Mercury. Its surface? Molten. Not lava exactly, but a global ocean of liquefied rock. Silicates, iron, magnesium, all melted into a churning, reflective sea that shines like polished metal. From space, this planet doesn't just reflect light, it blazes. It's so bright that if you pointed a telescope at its star system, you might mistake the planet for a binary companion star. Here's the feedback loop from hell. The star's light hits the planet's reflective surface and bounces back, but not all of it escapes into space. Some of that reflected light hits the planet's thin atmosphere and gets redirected back down. That light heats the surface. The hotter the surface gets, the more it outgasses, creating more atmosphere. More atmosphere means more light gets trapped. More trapped light means more heat. This is called a runaway albedo feedback, and it's the opposite of what usually happens. Normally, a brighter planet reflects more light and cools down. But get the conditions just right. High reflectivity, close orbit, specific atmospheric composition, and you can flip that script. The planet literally cooks itself with its own reflection. We've observed this effect in miniature on Venus. Venus reflects 75% of sunlight, and its thick atmosphere traps heat in a runaway greenhouse effect. Our self-cooking planet would combine high reflectivity with proximity to its star and just the right atmospheric feedback. Could it actually happen? Absolutely. We found ultra-hot Jupiters with dayside temperatures exceeding 4,000 Kelvin, hot enough to vaporize iron. Scale that down to a rocky planet with a reflective surface, and you've got a world locked in thermal battle with itself. Surviving there? Not a chance. But watching it from orbit, knowing you're seeing a planet caught in its own light trap, that's the kind of cosmic weirdness that makes you realize the universe is way stranger than we give it credit for. So, could you survive on any of these mirror worlds? Let's be honest. No. On the glass atmosphere planet, you'd be dealing with temperatures over 1,000 degrees Celsius. Your spacecraft would need a heat shield that makes NASA's Mars entry vehicles look like tin foil. The ice mirror ocean, you'd freeze in minutes without a heated suit. Plus, the psychological toll of infinite reflections. Actual sensory deprivation studies show that environments lacking visual variation can cause hallucinations within hours. And the self-cooking planet? You'd vaporize before you even reach the surface. But in orbit, with the right shielding and a good pair of polarized visors, you could observe these worlds. You could study them. And honestly, the view would be worth the risk. Just maybe don't look at your own reflection for too long. Before we wrap, let's ground this in reality. In 2023, astronomers using the James Webb Space Telescope confirmed that exoplanet JWST-96b has highly reflective clouds made of potassium sulfide. LTT 9779b, which I mentioned earlier, has an albedo of 80%, one of the highest ever measured. We've also discovered rogue planets like CFB-DSIR 2149-0403 drifting alone through space. Mirror worlds aren't just theoretical. They're out there. We're finding them. And with every new discovery, the universe gets a little weirder and a lot more beautiful. So that's mirror worlds, planets that reflect, refract, and trap light in ways that would make landing on them a nightmare, but watching them from space an absolute privilege. Next week, we're diving into something even stranger. Ocean worlds with floating continents, where islands aren't made of rock, but of ice, and they drift. But here's my question for you. Which of these mirror worlds would you want to visit? Would you risk the disorienting nightmare of the glass atmosphere planet? Walk across the silent, infinite ice mirror ocean? Or watch the self-cooking planet tear itself apart from orbit? Let me know in the comments. And if you want to see more of the craziest planets the universe might hide, hit that subscribe button. I'm Arya, this is Planetary Possibilities, and I'll see you next week.